We now continue with example 2, part A. We had already established algebraically that f is an even function and mentioned that the graph has y-axis symmetry. And I want to explain what we mean by y-axis symmetry. If we consider the points associated, say, with x equals 1 and x equals negative 1, you'll notice that they have the same y value. In other words, f of 1 equals f of minus 1. This is true for any pair of opposite x's I might select. F of x will always equal f of minus x. Graphically, what happens is if you draw a line segment connecting the 2 points, then the y-axis will act as a perpendicular bisector, meaning that the distance from the one point to the y-axis is the same as the distance from the other point to the y-axis. And this again would be true for any pair of opposite x's we might select. This is what is meant by y-axis symmetry. We can also just see from the graph how the graph is basically balanced on the y-axis. You might say that the left hand, the part of the graph to the left of the y-axis is the mirror image of the part of the graph to the right of the y-axis. So even functions always have this y-axis symmetry that I'm trying to describe. Let's look now at part B. G of x equals x over 1 plus x squared. Let's see if we can algebraically determine if g is even or odd. It all depends on looking at g of minus x. So replace x with minus x wherever you see it. And then simplify. So we'd have minus x in the numerator. In the denominator, we would have 1 plus x squared. The minus sign being squared makes it disappear. Notice what we don't get. We don't get the original function back again here. So we don't get g of x like we got with f of x in part A. We don't get the same thing back again. So apparently g is not an even function. So the next question would be, is g an odd function? For that, you look at the opposite of g of x, minus g of x. Minus g of x. That means we're basically putting a minus sign in front of x over 1 plus x squared. Now putting a minus sign out in front is identical to putting it in the numerator. With fractions, you can put the negative in front of the fraction bar, or you can put it in the numerator, or you can even put it in the denominator. So notice that what we have demonstrated is that g of minus x equals minus g of x. Therefore, g is odd. G is an odd function. So this is an odd function. And the graph of an odd function has symmetry about the origin. So the graph has origin symmetry. And what that means, and again, let me just use 1 and negative 1 to demonstrate this. Consider the points on the graph of g at negative 1 and at positive 1. Draw a line segment joining those 2 points. Well, I'm trying, but I'm having trouble. There we go. that line segment, if you have an odd function, will pass through the origin, and the origin will bisect the line segment. It will split it into two equal lengths. I apologize, my line segment isn't exactly the straightest line segment in the world, but I hope you get the idea. If I chose any other pair of x's that are opposites, I would see the same type of thing occur. That's what we mean by origin symmetry. Another way to look at it is that the right-hand part of the graph, if you reflect it across the x-axis and then again across the y-axis, it will correspond exactly to the left-hand part of the graph. So when you see that sort of thing occur, then you have a graph with origin symmetry and you have an odd function. Looking at our third example, part C, h of x equals x squared minus 2x. This is a parabola, as you can see. We'll study parabolas in much more detail when we begin chapter 3. For now, let's determine if this is an even or an odd function by evaluating h at minus x. So we have minus x squared minus 2 times minus x. We just replace x with minus x everywhere we see it, and we simplify. And simplifying, we get x squared plus 2x. Obviously, what we don't get is the original function. We don't get h of x. So this is not an even function. So you might think, well, if it's not even, then it must be odd. Well, not necessarily. You have to test to see if it's odd by looking at the opposite of h of x, minus h of x. Now, the opposite of h of x would basically be taking the opposite, or the minus, of all of x squared minus 2x. If we distribute the negative sign, that gives us minus x squared plus 2x. Minus x squared plus 2x. Well, what we are comparing that to, we want to know, is that the same as h of minus x? You can see it's not. We did h of minus x above, and you can see we don't have the signs quite the same. So this is not equal to h of minus x. So h of minus x does not equal h of x, nor does it equal minus h of x. Because neither of the definitions are satisfied, this function is classified as neither. H is neither even nor odd. So many functions are neither even nor odd. There are many functions that are even or odd, but many others that are not. Therefore, the graph should exhibit neither y-axis symmetry nor origin symmetry. That doesn't mean that the graph has no symmetry whatsoever. In fact, every parabola has symmetry about some vertical line. In this case, you can see from the graph that we don't have the axis of symmetry along the y-axis. Hence, it's not an even function. There's no point symmetry either, in the sense of having, say, symmetry about the origin. So there's no symmetry that we can really point to at this time in describing the graph of the function, although later we will talk about, as I mentioned, symmetry about a vertical line for the parabola. So for the time being, we just would not identify any symmetry for the graph. I'll just point out one other thing in closing. The reason we use the terms even or odd in describing these functions has something to do with the types of exponents we commonly see with even or odd functions. With even functions, we typically see even exponents. For example, I'll just write this off to the side here. If we have something like f of x equals x to the fourth plus x squared minus 2, for example, if we look at the exponents, we see they're both even. This turns out to be an even function. If we had the function g of x equals x cubed minus 2x, where both terms have variables raised to odd exponents, 3 and 1 in this case, then we would classify that as an odd function. However, just looking at exponents is not sufficient for determining whether a function is even or odd. You can see in part B of example 2 that we have a function where there's an odd exponent and an even exponent. G of x equals x over 1 plus x squared. So there's both an even and an odd exponent involved. It turned out to be an odd function, though. So you really need to be able to use the definition. Replace x with minus x and simplify and see where that leads. That's really the only definitive way to determine if a function is even or odd. Our final topic will be average rate of change. This is actually a very important topic when we move towards calculus. One of the main topics of calculus is the study of rates of change. And rates of change in calculus are studied beginning by looking at average rates of change. So let's talk about average rates of change and see how those would be defined. The average rate of change of a function f on the interval from a to b is f of b minus f of a over b minus a. Now, this reminds us, perhaps, of something that should be familiar to you from algebra. y2 minus y1 over x2 minus x1. Now, obviously, it looks a little different than that, but there is a similarity, obviously. In fact, the average rate of change, f of b minus f of a over b minus a, is just a way of writing slope using function notation. So what you see there is indeed a slope. It's just that we're using function notation to describe the change in the difference in the y's rather than using, say, y2 and y1. So note that the average rate of change is identical to the slope of the line passing through the points a f of a and b f of b. So the average rate of change of a function is the slope of a straight line connecting 2 points on the graph of the function. Now the function itself does not have to be a straight line, but the average rate of change itself is the slope of a straight line. I don't have enough time to go further with this video, so we'll continue with the third video with example 3.